Um, Thank you all. Welcome to the Mentored Research project presentations. Professor Kim is not able to join this evening. I believe he's traveling. The IonQ team is here. Your mentors are here, Miguel and Luning. I'd like to ask the first presenters to get ready to show their presentations. This is Miguel's team. It's called PosKet, and they're going to give a presentation on efficient loading of classical images into quantum states. I'll pass it over to you, and you can put up your slides and begin your presentation when you're ready.
Okay. Can you see my screen?
I can see your screen. You're not in presentation mode, so I don't know if you want to pop it into that, but otherwise it looks good.
Is my voice is okay?
Yep, you sound loud and clear.
Okay. Hello, I'm Chang-Soo Kim. I'm the member of Team PosKet, and Do-Hoon Kim is the leader of our group, and Sung-Bin Kwon is another member of our group. I'm going to talk about efficiently loading classical images into quantum states, and Dr. Ruiz gave a guidance about this project. So before I talk about our approach, I will first introduce about the background and motivation, and then I'll talk about our method and talk about some experimental results. First, these days, quantum machine learning gets popular. So, and the necessary process of quantum machine learning will be quantum state preparation. Quantum state preparation is like this. If we construct a certain quantum circuit, and then we can obtain the original state by running this quantum circuit with 0 states. And it is widely known that the depth of a quantum circuit will increase exponentially without ancillary qubits, and we can reduce the depth to polynomial size using exponential ancillary qubits. Before I talk about our approach, I will talk about some tensor concepts and some MPS. Tensor is a special way to describe multidimensional matrices, and we have special graphical notation to describe tensor networks. So vector and matrices are all tensors, and we can describe it as just one circles and another dangling edges. The advantage of using this notation will be we can easily describe a matrix multiplication process like this. Because both of them are tensors, we can express a product of tensors like this figure. And I will briefly talk about some MPS decomposition based quantum state preparation, because our approach is highly inspired by this algorithm, and then we are going to improve this algorithm. So as you can see, those are a combination of tensors, and it is equivalent to the original state that we want to load on a quantum computer. And after we truncate these combinations of tensors using a certain algorithm, we can obtain quantum circuits correspond to these original data. And the obtained quantum circuit, the obtained one layer of quantum circuits will be added like this. And then by repeating this kind of process, we can obtain our final quantum circuit that maps a zero state into our desired state. So, and the limitations, one of the limitations of this method will be, we need to repeat this kind of process with the number of data. So for example, if we have 10,000 images and we will train the quantum CNN using those data, we need to because we need to first prepare the states, we will have 10,000 quantum circuits for each original states. So we thought that this kind of process takes a lot of time and consume resources. So we will propose some machine learning based state preparation. Because it has general neural networks in the middle of the, say, preparation process, we can generate those quantum circuit by easily inferencing the original classic data. And then I'm gonna introduce our approach. Our model structure is shaped like this. And we designed the model that transforms classical data into parameterized quantum circuit parameters. So we can first using data quantum encoder and decoder, and then we will obtain the final quantum circuit. And then the final goal of this process is to maximize the fidelity between the original data and the final data. So first, we implemented data encoder. It abstracts some important feature of the classical data to and make the latent vector z, and the length of this vector is shorter than original classical data. And this can be obtained with autoencoder algorithm, and then PCA and other some data encoding algorithms. And then we implemented decoder. And decoder receive an input as latent, receive a latent vector input, the shortened vector, and then it generates parameterized quantum circuit parameters that will be used in constructing the final quantum circuits. If we obtain parameters after PQC decoder, we will apply those parameters into our quantum circuits, and then we used a special kind of structures, and I will talk about it later. So this is the training process of data encoder. First, we prepare input data, and then we generate a latent vector, and we also made the data decoder for the reconstructed data, and then we trained these both circuits using these matrix because this means we will reduce the distance between reconstructed data and input data so that we can improve the fidelity. And this is the process of training PQC decoder. As you can see, this data decoder is for just for training data encoder, and this is the decoder we will use. In this process, we will first freeze the data encoder to prevent from forgetting learned knowledges. And in this process, we have tried a lot of matrix, and this is one of the matrix that generates the high fidelity. We use infidelity rather than fidelity to reduce this matrix. And then we fine-tuned both data encoder and decoder. And in this process, there is a slight update on data encoder to make it optimized to the task. And we used infidelity in this process. So it is an experimental result, and we use Intel CPU, and we use penny lane software and PyTorch. And the data set we used is MNIST data, and it consists of 10,000 training images and 1,000 test images. As I mentioned, we used special kind of circuit structures, and because each 2-qubit gate must be unitary, we use this formula to maintain the unitarity. Because all of the parameters will be in a real manifold, so we will use standard rotation gates, and then by introducing those 6 parameters, we can easily obtain one unitary 2-qubit gates. And the number of layers will be 5 or 10. It depends on the performance. So this is the real implementation of our encoder and decoder. The image encoder is simple neural network, and then decoder is simple. The basic code of the decoder is the simple neural network, and then we added another optimization techniques on these encoder and decoder. Yeah, this is the result. Compared to MPS-based method, we obtained quite similar result in terms of fidelity. When the layer is 5, we can obtain the 0.78, around 0.77. And then if we use layer 10 layers, and we can obtain 0.83 and 85. It's kind of similar. The advantage of our algorithm will be shown in this slide. Because if we run MPS-based method, we will spend a lot of time running the algorithm, because it will generate each layer and then optimize its gate, optimize the layer gate by gate. But if we use machine learning based algorithm, we can just inference our data and then obtain the parameters, and then apply those parameters into our parameterized circuit. And this is the image of this is the loaded image of MNIST data. As you can see, it is the obtained result is kind of similar when we use the same number of layers. And as you can see, there are slightly improved images in the below, because we used 10 layers to improve the fidelity. So we proposed and implemented a machine learning approach for efficient quantum state preparation compared to MPS-based method. We introduced encoder-decoder structure, and it converts data to parameter, and it used effective training strategy. So in conclusion, our method achieved comparable reconstruction fidelity with faster runtime compared to the previous work. Our future work will be like this, because we implemented it as small MNIST image. We need to extend it to large image data sets with higher resolution. And we will use some other data sets in different domain, like finance data. And then we will use the flexible structure. And then one of our goal will be obtaining not only obtaining the parameters of our circuits, we can obtain the number of layers while doing the while running the encoder decoder structures. And then we can also adding some optimization technique, which is widely used in MPS-based method. Thank you for listening, and thank you for Dr. Ruiz to manage our project.
Thank you very much. I'll open the floor to questions. Anyone have any questions? I encourage either mentors or guests to ask questions. Okay, I have a question. You won't get away that easy. When you went, you mentioned, I think in your second to last slide, oops, sorry,
Okay.
the conclusion one, it said, I think it was somewhere you said you added another layer to the neural network, and you got improved results, I think.
You mean we obtained the improved result by adding layers?
Yeah, I guess my question is, if at what point are you almost overfitting, like, using too many parameters versus like if you just keep adding layers to your model, will it continuously improve, but that's not real improvement?
Yeah, right. Yeah, that is one of the concerns that we have, because in these small layers, we could actually get a quite good result. But if we add layers, I think there will be overfitting problem, so that some of the numbers will generate it correctly, but some of the numbers will not. So yeah, I think we need to add some method to prevent overfitting.
Thank you. Last call for questions.
Can you, a great presentation, by the way. So do you think you will have much different results for the tensor network part if you use some optimized libraries, for tensor network, or do you think that would be, not really important?
So you mean the scalability of our method, right?
Yeah, I mean, yeah. So I guess that there's probably different packages that optimize tensor contractions and multiple, tensor operations. So I'm guessing that if I don't know, do you think that that would have an impact? Yes, yeah, if you scale this.
Yeah, because we constructed the quantum circuit like this, I think we can add some optimization technique that is widely used in current papers, so that we can improve our result using the technique. And yeah, what we have done is we made the how can I say? So we made this process really convenient. So if we add some techniques that are used in other MPS-based method, I think we could get an improved result.
Okay, I see. Thanks.
Thank you.
Thank you very much, and great presentation. If you can unshare your screen, I'll invite the next group. Thank you again. Sorry,
you.
I want to go back. So next up is another one of Miguel's teams. It's called Quantum Physics Ed, Qp.Ed, and they're going to discuss development of quantum physics teaching and learning program based on the 2022 revised curriculum. So if you can, excellent, you have your slides up already. I will turn it over to you, and then we'll have questions at the end.
Hello. Can you hear me? Yeah.
We can hear you, and your slide it looks good.
Thank you so much. Yeah, I'm Taekyung Lee, and I will present about the development of education program on quantum physics education based on South Korean revised curriculum. And I also uploaded the presentation material in chatting. Our team is me and Gunoo Lee, who is in this Zoom, and Hyunju Yoon, and our mentor is Dr. Miguel. And as my English is not very good, I present in Korean. Yeah. 네, 한국어로 발표를 하도록 하겠습니다. 닥터 미구엘과 함께 2022 개정 교육과정에 근거한 양자물리학 교수학습 프로그램 개발 프로젝트를 진행한 이태경, 이근욱, 윤현주입니다. 저희 팀은 물리교육 연구자와 물리교사로 이루어진 팀입니다. 네, 이 순서로 발표를 진행할 텐데요. 먼저 이제 연구의 필요성에 대해서 말씀을 좀 드리고, 교육과정이 이번에 개정이 되었거든요. 2022년에 개정이 되었는데, 아직 이제 학교 현장에서는 시행은 되지 않았고요. 그래서 교육과정 개정 간단히 말씀드리고, 주로 저희 멘토링 활동에서 교육과정의 어떤 성취 기준을 어떻게 재구성할 것인가, 그리고 이 내용을 가르치기 위해서 어떤 내용이 필요할 것인가, 그걸 이제 분석을 했기 때문에 멘토링 활동에서 주로 이루어진 활동을 말씀을 드릴 거고요. 이어서 향후 과제를 위한 제언점을 좀 발표하도록 하겠습니다. 먼저 연구의 필요성입니다. 여기 계신 분들 다 저보다 잘 아실 텐데요. 양자 컴퓨터 기술의 발전이 최근 눈부시게 이루어지고 있고, 또 이제 재작년에 양자 관련 노벨상을 받았던 물리학상으로 노벨상이 나왔던 배경도 있을 것 같습니다. 국내에서는 국가 핵심 전략에 관한 특별법을 좀 개정하기도 하였는데요. 거기에 10대 기술 중에 하나로 양자 기술이 포함되기도 하였습니다. 이처럼 우리 사회는 양자와 관련된 과학 기술에 집중을 하고 있습니다. 그리고 이렇게 사회가 변화함에 따라서 양자랑 관련된 교육이 이루어져야 될 필요성도 좀 덩달아 높아지고 있고요. 그래서 이제 고등학교 교육 과정에서도 양자를 배우기에 가장 가까운 과목인 물리학 과목에서 양자 관련 내용이 이번 교육과정 개정에서 크게 증가했습니다. 그리고 이제 재작년에 공표된 2022 개정 교육과정에서는 물리학의 한 과목으로 전자기와 양자라는 과목이 신설되기도 하였는데요. 이렇게 이제 물리교육에서 이뤄진 몇몇 연구들을 좀 같이 살펴보면은 학생들은 양자물리학에 관해서 흥미를 많이 갖고 있고, 또 양자물리를 배우는 게 본인들의 커리어라던가 향후의 진로에 도움이 많이 될 거라고 인식하는 경향을 보이고 있습니다. 그런데 양자물리학을 공부하는 것을 또 어렵다고 인식하는 경향도 나타나고 있습니다. 사실 학교에서 학생들이 배우는 과목은 양자물리뿐만 아니라 다른 과목들도 다 어렵거든요. 전자기학도 어렵고, 물리학도 어렵고, 물리뿐만 아니라 화학이라던가 다른 과목들도 다 어려운데, 근데 어려운 과목을 공부할 때 학생들의 학습을 촉진하는 그런 역할을 하는 게 물리교사거든요. 그런데 이제 양자물리학에서 유독 학생들이 어려움을 호소하고 있는 데에는 물리교사들의 학습의 촉진자 역할을 하는데 좀 어려움을 겪고 있을 거라고 추측을 할 수 있죠. 실제로도 한 연구를 보면 물리교사들은 양자물리학을 가르치는데 어떤 어려움을 겪고 있는데 연수가 부족하다던가 아니면 학습 자료가 좀 부족하다던가 이런 어려움을 호소하고 있었습니다. 네. 그래서 이제 양자물리학을 제대로 이제 고등학교에서부터 가르쳐 주려면 이렇게 교사들을 좀 지원을 해서 좀 교실에서 교육이 잘 이루어지는 게 필수적으로 좀 이루어져야 되겠죠. 그래서 저희 팀은 교수학습 프로그램의 개발에서부터 이렇게 문제를 좀 해결하고자 했습니다. 그래서 양자물리학 교수학습 개발을 집중적으로 저희 멘토링에서 실시를 했는데요. 양자물리학 교수학습 개발은 실제로 교실 현장에서 실용적인 필요성 외에도 물리교육 연구 쪽에서 물리교육이라는 분야에서 필요로 하는 어떤 학술적인 방향으로서 필요로 하는 연구이기도 합니다. 네, 그래서 이제 교육과정 개정에 대해서 간단하게 좀 말씀드릴 텐데요. 최근에 이제 교육과정 개정을 어떤 내용이 좀 추가되었고 어떤 내용이 바뀌었는지가 좀 논문으로 나왔던 게 있어서 그걸 이제 같이 소개를 드리고요. 여기는 이제 성취 기준인데 원문을 좀 최대한 살리고자 한국어로 가지고 왔습니다. 그래서 여기 2015 개정 교육과정과 오른쪽에 2021 개정 교육과정을 비교해 볼 수가 있겠는데요. 2015 개정 교육과정에서는 과목이 물리학 1과 물리학 2 이렇게 구성이 되어 있습니다. 그래서 요거 성취 기준 하나하나를 가지고 왔는데요. 성취 기준이 물리학 1에서는 2개가 있고요. 물리학 2에서는 3개의 성취 기준으로 이루어진 것을 확인해 볼 수가 있습니다. 그 다음에 2022 개정 교육과정에서는 피직스랑 일렉트로매그네티즘 앤 퀀텀 피직스라고 한 이 두 가지의 교과로 좀 생각을 해볼 수가 있겠는데요. 이 물리학 1에 해당하는 게 물리학으로 바뀌고 물리학 2에 해당하는 게 이 두 번째 이제 전자기와 양자라는 교과로 바뀌었다, 대응된다라고 생각하시면 될 것 같습니다. 그래서 이제 기존의 2015 개정교육과정에서는 2개의 성취 기준이었는데 2022 개정교육과정에서는 3개로 늘어났고요. 여기서는 3개의 성취 기준이 6개의 성취 기준으로 학습량이 확 늘어난 것을 확인해 볼 수가 있습니다. 왜냐하면 이 성취 기준의 개수가 실제로 교실에서 수업을 할 때 시수랑 비례하도록 교육과정을 만들게 되거든요. 네, 그래서 2022 개정교육과정에서 지금 6개의 학습 요소를 좀 소개를 드렸었는데요. 요거를 이제 영어로 같이 좀 설명을 드려야 될 것 같아서 네, 양자와 관련된 것들을 영어로 번역해서 이렇게 6개를 좀 제시를 했습니다. 첫 번째인데요. 첫 번째 성취 기준은 네, 여기 빛과 물질의 상호작용에 관련된 광전 효과와 관련된 성취 기준이고요. 그다음에 두 번째는 네, 레이저의 학습을 하면서 레이저의 원리와 네, 여기서 이제 증폭의 원리를 배우게 되는 그런 학습 내용이고요. 그 다음에 세 번째로는 입자와 파동의 이중성을 이중슬릿 실험으로 학습하는 그런 성취 기준이고요. 그 다음에 네 번째, 요게 이제 좀 새롭게 들어왔는데요. 양자 컴퓨터라던가 양자 암호 통신이라던가 뭐 양자 암호 이런 기술들이 새롭게 이제 우리 사회에 도입됐을 때 우리 사회가 어떻게 변할 것인가 요걸 이제 배우게 되는데 여기서 중첩과 네, 중첩의 원리를 이용해서 양자 컴퓨터가 어떠한 핵심 원리로 이루어지는 것이고 양자 컴퓨터의 도입으로 인해서 기존의 암호 체계가 왜 바뀌어야 되는지 그런 내용을 학습하도록 되어 있고요. 그 다음에 양자 터널링에 대한 내용도 이제 새로 들어오게 됐습니다. 양자 터널링 같은 경우는 이전에는 2015 개정교육과정에서는 고급 물리학이라고 해서 뭐 공동교육과정이라던가 몇몇 좀 선택적으로 이뤄진 학교들에서만 이뤄지고 있던 교육이었는데요. 지금은 이제 모든 학교에서 수업할 수 있도록 이렇게 좀 되었습니다. 정규 교육과정으로 기존에도 정규 교육과정이었는데 선택 교육과정이라기보다는 모든 학교에서 열릴 수 있는 형태의 교과로 이제 편성이 되었고요. 네, 마지막으로는 이건 이전 교육과정에서도 같이 있었던 건데요. 불확정성 원리를 바탕으로 해서 현대 원자 모형을 이해할 수 있도록 하는 학습 내용이 이렇게 이제 도입이 되었다. 이렇게 보실 수가 있을 것 같습니다. 네, 그래서 저희 그 멘토링 활동에서 크게 이제 두 가지를 했는데요. 먼저 요 6개의 성취 기준을 가르치려면 어떤 순서로 가르쳐야 되는가에 대한 논의를 했고, 요 6개의 성취 기준을 가르칠 때 구체적으로 무엇을 가르쳐야 되는지에 대한 논의를 했습니다. 그래서 요 첫 번째로는 어떤 순서로 가르칠 것인가인데요. 제가 이제 방금 소개해드렸던 거에서 여기 첫 번째와 두 번째 성취 기준과 네 번째와 다섯 번째 성취 기준에서 순서를 좀 바꿔서 가르치는 게 더 도움이 되겠다라고 이제 디스커션을 좀 진행했습니다. 왜냐하면 레이저에 관한 내용이 먼저 앞부분에 나오게 되면 학생들이 실생활에서 레이저를 접할 일이 좀 많기 때문에 조금 더 학생들의 동기를 유발하고 흥미를 유지하면서 학습을 할 수 있도록 하겠다라는 아이디어가 좀 있었고요. 그 다음에 양자 터널링과 양자 테크놀로지에 관한 성취 기준을 바꿔서 이제 가르치게 되면은 네, 양자 컴퓨터에 대한, 그러니까 그 양자 컴퓨터에 대한 내용을 배울 때, 그 반도체를 작게 만드는 게 좀 터널링 때문에 좀 어렵잖아요. 그 양자 터널링의 문제를 양자 터널링에 대한 학습을 하면서 반도체를 소형화시킬 수 없는, 그러니까 더 이상 이제 더욱더 작게 만들 수 없는 문제를 가르치면서 같이 이제 양자 컴퓨터에 대한 내용으로 넘어올 수 있을 거라고 이제 디스커션을 하면서 이렇게 순서를 좀 바꿔서 수업을 하도록 아이디어를 좀 내봤습니다. 그 다음에 이어서는 그 각각의 성취 기준에 대해서 어떤 내용을 어떻게 가르칠 것인가 에 대한 이야기를 좀 했었고요. 여기서는 간의 학습 위계 분석이라고 하는 걸 통해서 분석을 했습니다. 이 내용은 제가 PPT에 실지는 않았고요. 이렇게 이제 네. 저희가 작업한 내용을 그대로 좀 보여드릴 수가 있을 것 같아요. 일반적으로 교육 프로그램을 만들 때 선행적으로 이루어지는 작업입니다. 학습 과제 분석이라고도 하고 저희가 이제 했던 건 학습 위계 분석이라고도 하는데요. 여기 보시면 까만색 박스로 되어 있는 게 방금 전에 소개드렸던 6개의 성취 기준이고요. 여기 붙어 있는 메모들은 저희가 디스커션을 하면서 적어놓은 내용들입니다. 그 중에 하나만 좀 소개를 드릴 텐데요. 요게 이제 레이저에 관한 학습입니다. 그래서 요 학습을 위해서 이루어져야 되는 게 레이저에 관한 원리가 가르쳐져야 될 것 같고 레이저의 특성이 가르쳐져야 될 것 같고 레이저의 활용 예시를 가르쳐야 될 것 같다는 이야기를 좀 했고요. 그 다음에 이제 레이저의 요 응용부터 좀 말씀을 드리면 레이저의 응용은 뭐 산업 분야의 응용과 교육에서의 응용 그리고 과학 연구에서의 응용을 좀 생각을 해봤습니다. 그래서 어떤 것들이 학생들의 동기를 유발할 수 있을 것인가에 주안점을 맞춰서 좀 디스커션을 했고요. 이전에 교과서라던가 다른 자료에서 소개하고 있는 레이저의 활용도 같이 참고를 했습니다. 그래서 요 세 가지 분야로 나눠서 레이저가 어떤 분야에서 그리고 어떤 분야에서 활용되고 있고 학생들이 흥미를 가짐하는 것이 무엇인지에 대한 이야기를 바탕으로 해서 레이저의 특성을 같이 가르칠 수 있도록 좀 아이디어를 좀 내봤고요. 레이저의 특성으로는 4가지를 좀 생각을 해봤는데 이게 궁극적으로 그 유도 방출을 가리키기 위한 것이다 보니까 유도 방출과 관련된 특성들만 좀 뽑아서 학생들에게 가르치는 게 좋지 않겠느냐 이런 이야기 아이디어도 좀 있었습니다. 그래서 레이저의 특성 중에서 하이 인텐시티와 요 단파장성 요 2가지를 중심으로 해서 유도 방출이라고 하는 레이저의 원리로 좀 학습을 연결짓는 게 좀 가능하겠다라고 이야기를 했고요. 여기서 유도 방출을 하면서는 이게 실제로 교실에서는 수업을 할 때 실험을 같이 하면서 하기가 어렵기 때문에 가상 실험을 통해서 가상 실험에서 에너지가 방출이 되고 같은 에너지가 방출이 되면서 같이 이제 원자가 에너지 레벨이 떨어지게 되고 그런 과정을 학습하면서 요 레이저의 원리를 배울 수 있겠다고 생각을 했습니다. 네. 이런 식으로 이제 디스커션을 진행하면서 각각의 성취 기준에 대해서 뭐 가르쳐야 되는 내용들을 유목화를 시켰고요. 그다음에 여기서는 또 이제 성취 기준과 성취 기준 중에서 연결될 수 있는 부분들이 있는 것 같아서 이런 식으로 성취 기준을 연결하면서 학습의 흐름을 재구성하기도 하였습니다. 네, 이런 식으로 디스커션을 했고요. 네. 그래서 이제 요거는 저희가 일단은 만들어 본 몇 개의 작은 수업 지도안을 좀 소개를 드릴 수 있을 것 같습니다. 일단은 큰 프로젝트를 주제를 정했고요. 여기서 이제 과학 뉴스 기사를 학생들이 양자물리학과 관련된 과학 뉴스 기사를 학생들이 작성해보는 하나의 큰 프로젝트를 가지고 각각의 성취 기준을 이 안에다 포함시킬 수 있을 거라고 가정하고 여기 프로젝트 기반의 학습을 좀 만들어 봤습니다. 그래서 먼저 이제 제가 레이저를 계속 설명을 드렸으니까 레이저로 여기서도 같이 설명을 드릴 텐데요. 여기 성취 기준 적어놨고요. 그 다음에 여기 디테일이라고 되어 있는 부분 학습의 흐름을 간략하게 적어놓은 내용입니다. 네, 디테일인데 간략하게 네, 제가 적어놨죠. 네, 여기 보면은 먼저 네, 학생들의 레이저와 관련된 경험을 좀 나누면서 좀 시작을 하고요. 여기서 또 한 가지 좀 이슈를 제안을 합니다. 지금은 우리는 그 레이저가 만 19세 미만한테 판매가 금지되어 있는데 예전에는 레이저로 인한 실명 문제가 좀 있었죠. 실명 문제라던가 뭐 산업 분야에선 레이저로 인한 사건 사고도 좀 일어나고 있는 것 같습니다. 그래서 이런 사건 사고들이라던가 일상생활이라던가 우리 사회 곳곳에서 보이는 레이저와 관련된 이슈를 소개하면서 학생들의 흥미를 유발하고 그 다음에 레이저에 관한 특성에 대한 네, 수업으로 넘어가고요. 그 다음에 여기서 레이저의 고강도성으로 넘어갑니다. 사실은 여기서 발생하는 문제들이 고강도성이라고 하는 특성 때문에 나타나는 특징인 거죠. 그래서 네, 여기서 방금 전에 설명드렸던 가상 실험을 통해서 레이저의 특성을 레이저의 원리를 학생들이 말하도록 하게 하는 수업이 이어지게 되고요. 마지막으로는 이 유도 방출이라고 하는 원리를 교사가 설명하면서 네, 다음 학습으로 넘어가게 되는 흐름으로 수업을 좀 짜봤습니다. 네, 이런 식으로 이제 광전 효과에 대한 것도 비슷하게 좀 짜봤는데요. 여기서도 각각의 그 학습 성취 기준에 적절한 가상 실험을 저희가 하나씩 좀 탐색해보는 시간이 있었고, 이제 양자물리학 같은 경우는 실험을 통해서 배우는 게 교실에서 하기 되게 어려운데, 고전역학이라든가 전자회 같은 경우는 그래도 이제 실험을 통해서 하는 게 가능하지만 양자는 좀 어렵잖아요. 그래서 이런 부분들을 좀 극복하고자 가상 실험을 통해서 네, 학습할 수 있도록 좀 아이디어를 좀 내봤고요. 네, 네, 이런 식으로 해서 네, 요 두 가지 정도의 네, 성취 기준을 프로그램을 좀 소개를 드릴 수 있을 것 같습니다. 네, 그래서 이제 네, 여기서 저희한테 이제 더 이상 앞으로 이제 해결해야 될 문제는 지금 이제 학습 내용들을 분석을 하면서 내용을 가지고서는 수업을 짰지 여기 교수학습적인 어떤 교육학적인 이론이 깊게 들어가 있지는 않았는데요. 지금 저희가 만든 프로그램에다가 앞으로는 교육학적인 이론을 접목을 해서 조금 더 수업 프로그램을 탄탄하게 만들어야 될 필요성이 좀 있을 것 같습니다. 그래서 요 수업을 실제로 교실에다가도 투입을 하고 거기서 또 학생들이 어떻게 학습하는지 학습 효과를 분석함으로써 요 프로그램의 효과를 좀 같이 분석할 수 있을 거라고 생각을 하는데요. 지금 수업을 해줄 수 있는 교사는 2명 정도 좀 섭외를 해서 2개의 학교에서 시행이 가능할 것 같은데 그게 이제 2학기에 아마 시행이 될 것 같거든요. 그렇기 때문에 남은 기간 동안 교육학 이론을 적용해서 교수학습 프로그램을 조금 더 탄탄하게 하는 게 저희의 과제가 될 것 같습니다. 네. 이 내용들을 참고했고요. 발표는 여기까지 해서 마치도록 하겠습니다. 감사합니다. Thank you.
Thank you for the talk. I had one question, if that's okay.
Yeah, sure.
Do you know why they compared a German curriculum to a Korean curriculum? What was the reason for those two countries?
The research is the one that I joined and one German researcher, the physics education researcher, contacted us to compare the curriculum because the German physics curriculum is also revised in 2022.
Mm-hmm.
Yeah, and the industrial structure or the social atmosphere for the education is very similar. Yeah, so we compared the two countries' curriculum and the textbook. So we could find that what kind of things the difference of things that students learn from the school curriculum and how they are taught in classroom by analyzing the textbook.
Thank you.
Thank you.
I'll open up questions for the rest of the group. Any questions for this team? Last chance, last call.
So I have a question. Are there any plans to implement this program on a school anytime soon?
Excuse me?
Yeah, do you have or are there any plans to implement this project, this plan on a school, anytime soon?
Yeah, exactly. I present in Korean. Yeah, so we have planned to implement this program to the real high school classroom in autumn, September and October. We gathered 2 physics teacher, and so totally maybe 100 students will experience 100 or 150 students will experience our program, and by analyzing the result of student learning, we will analyze the effect of this program. Yeah.
Great, thank you. And
Thank you.
Thanks for the talk. It was a very nice talk.
Oh, yeah. May I have one question?
Please.
Oh, okay. Thank you very nice talk. I wonder, is there any classical mechanics parts? So this talk mainly covered the quantum mechanics and electromagnetism topics. So I wonder the remaining parts, classical mechanics, these parts are still similarly charged in the future curriculum, or there is also some changes in future curriculum?
The whole curriculum is revised, and I just introduced the part of quantum physics.
Okay.
Do I
Yeah.
understand well your question?
Yes. And okay, thank you.
Thank you again. I'll get ready for the third team, and this is 5 Ryan. It's Luning was the mentor, and the title of this presentation is VQNHE implementation and error mitigation using convolutional neural networks. I can see your slides. You haven't said anything yet, so we'll test that in a second.
All right. Do you hear me well?
Yeah, I hear you well. Do you want to put your slides in presentation mode? Yes, thank you. They look good.
Great. Is it in a presentation mode?
Yes, it is.
All right, great. Just a second, please. Let me just start my video. All right, do you see me well? Just a second, please. Just put my background. All right. Hi, welcome everybody to our presentation about error mitigation on VQE using artificial neural network. And our team name is Orion. It might not be familiar to people who are not familiar with Korean language because number 5 is read as O in Korean. So it is basically Orion. So, my name is Minho Kim. And our mentor is Luning Zhao, and we have conducted a research regarding how dealing with errors on a variational quantum eigensolver using artificial neural network based on a brilliant paperwork. So our research consists of 3 main parts. First one being an introduction of variational quantum neural hybrid eigensolver. And we have searched on the effects of VQNHE on variety of errors. And finally, we have adapted a convolutional neural network on top of it to deal with those error sources in a much better accuracy. So first and foremost, what is VQNHE? It has been conducted in a very, it has been uploaded, a brilliant paper has been uploaded in 2022 regarding VQNHE. And the whole scheme is to attach a neural network on top of variational quantum eigensolver to yield a much better performance. And it consists of 4 main parts. The first one being parameterized quantum circuit, and second one being a measurement circuit. And the author of this paper suggests a concept of star qubit. And that star qubit plays a role in putting inputs into a neural network and getting the overall Hamiltonian's expectation value. So first, parameterized quantum circuit is responsible of preparing a standard ansatz circuit. So it is nothing different than our original VQE circuit in a sense that it prepares hardware efficient ansatz. And following the ansatz circuit is a measurement circuit. So depending on a policy chain on which you evaluate, you apply adequate transforms according to the letters. So if the Pauli string consists of identity or Z letter, you just leave the gates. But for the Z letter, if the measured value is 1, you just adjust the sign. And for X and Y letters, you apply Hadamard and pi/2 rotation along the X axis. And like I mentioned, there is this concept of star qubit. So star qubit is the first qubit that corresponds to a letter X or Y of the Pauli string. And if there is no letter X or Y, there is no such star qubit. And the role of this star qubit is that the measured value of star qubit, whether it being 0 or 1, determines the sign, overall sign of each bit string when we evaluate the expectation value of Hamiltonians. Detailed, technical conversations regarding this topic is not the main part of our presentation, so we'll just if anyone wants to study deeper into this topic, please refer to the paper that has been published. And last but not least, we have the neural network that is attached onto the bit string. So it takes a bit string information as an input at every measurement and yields a single value fs that corresponds to each bit string. So you have an input bit string that is, for example, length 5, and you apply a fully connected network along with a ReLU activation to yield the first hidden layer, another FCNN layer, and a sigmoid activation function to yield a second hidden layer, and you apply a weighted sum with an exponential hyperbolic tangent function to get to the final destination of Fs. And this structure has been proposed in a in a paper, but the author does not explicitly describe why they have used FCNN or these these hyperparameters to construct a neural network. So we have investigated this part in much more detail. So to summarize, it effectively improves the performance of the standard VQE without using any additional quantum resources or attaching a lot of ancillary qubits. And it only uses a polynomial order classical resources because it takes in a bit string as an input. So the length of the bit string is equal to the length of the number of the qubits. So it doesn't really increase the throughput. I mean, it doesn't really increase the necessary resources that the algorithm needs, and it yields much better Hamiltonian, especially under the existence of errors. So this to test this scheme, we have tried a 5-side transverse field Ising model in a open boundary conditions, and we have utilized this hardware efficient ansatz to get this result right here. So the graph on the right side shows the result under a variety of error sources, and under a lot of errors we could clearly see that VQNHE yields much lower energy compared to original VQE. And I don't think we see the line here. The exact eigenvalue was around -6.02 in this case, as you see on the left side aligned with the orange line. And VQNHE really seemed to converge to that exact value much better than using just the VQE circuit alone. And we also tried for 12-side transfer field Ising model, which also worked pretty well, as you can see on the right side. So then, moving on to the second part. It works well. It's all good. But why does it work? How does it improve the optimization result? We try to reason this out by, looking deeper into the role of the neural network, because we all know that VQE works. But what does neural network actually do? Does it expand the expressible states of the ansatz circuit? Does it generate something new? Does it accommodate, some new data that were hidden in the VQE, or does it handle errors well? The answer to this question of our group is that it does so by mitigating errors. So if you see the original variational quantum eigensolver formula, you just and compare it to VQNHE. VQNHE's neural network part transforms the original quantum state into another quantum state. And if there is some error sources that transform this original phi to some undesired state, neural network might be responsible of putting back that state into the original state and By that, I mean, it mitigates errors and yields better results. And to test out this scheme, we have tried on several error sources shown here. We have tried on depolarizing errors that randomly decays the density matrix into identity, and bit flip errors that randomly flips certain bits, and also damping errors that shrinks the density matrix overall. And the result is shown here. We have used the same structure that the paper used. And one interesting, well, first of all, it clearly lowers the energy compared to the original VQE, and it really works to mitigate errors. But one interesting fact is that it especially does it well in case of bit flip errors. And the reason why it does well for bit flip errors is pretty clear if you think about the architecture of this transformation. Say, for example, you have a bit flip channel that flips this 0, 0, 0 state into other states with certain probabilities. In this case, if this transformation leaves 0, 0, 0 to 0, 0, 0 95% of the time, and if the neural network is responsible of sending 0, 0, 1 state to 0, 0, 0 state with 2% of probability, and 0 and 0 to 0, 0, 0 and 3% of probability. This works completely in an opposite way of bit flip channel when we think about the expectation value, because expectation value takes this problem in a aggregate way. So you sum up all the behaviors, and at the end of the day, the neural network might compensate for the bit flip channel. So it does exceptionally well for bit flip errors, and it really does seem to mitigate errors quite well. But then we found some problem here. And this brings on to the next part of our presentation, VQ&HE with CNN structure. Okay, so previous 3 types of errors, which are depolarizing errors, bit flip errors, damping errors, were all non-unitary error sources. So they just make those error sources collapse in a certain way. But what are actually major error sources? And since we were dealing with superconducting qubits, sorry to IonQ, but we were dealing with superconducting qubits that works on IBM backends. The major error sources did not actually come from non-unitary errors, but rather in unitary errors, especially the crosstalk terms, which occur as the result of coupling between 2 neighboring qubits. So this particular experiment, is regarding crosstalk suppression, and it really improves the performance only by suppressing crosstalk, which means that this particular error source is responsible of generating large amount of errors. And sadly, the original structure that was proposed in the VQ&HE paper did not seem to handle these unitary errors quite well, especially the crosstalk errors. So, and the reason is that when you see this structure in superconducting qubits, the connectivity is each qubit is only connected to 1 or 2 neighboring qubits, or even 3. But the state of the qubit 0 is not really affected by state of qubit 4 as much as it does for qubit 1. So we can clearly tell that the amount of error depends on the state of adjacent qubits, just like this. And as it depends on the state of adjacent qubits, instead of using the standard structure of neural network, we thought that it might be much helpful if we use a convolutional neural network, which mostly deals with the behaviors of adjacent qubits. And for those of you who are not who are not a big fan of convolutional neural network, it introduces this window called kernel, and it swipes through the data to yield a weighted sum instead of using the entire vector as the candidate of a sum. So this is our revised structure of CNN to be attached onto a variational quantum eigensolver. So we have utilized two sizes of kernels to accommodate variety of error sources, but the most important kernel is the one with size 3, so that each qubit is so that we assume each qubit is affected by its two neighboring qubits. And we also have activation layer, same as previous one. And the last layer right here is the same layer that we have the original paper uses. And the performance is quite satisfying. Before heading to the unitary error channel, we have to assure that convolutional neural network also works for non-unitary error sources as well. And as you can see here, convolutional neural network effectively lowers the energy compared to the VQE, and it shows similar performance compared to the fully connected network structure that was proposed in the paper. And surprisingly, for crosstalk errors, a fully connected network, as the crosstalk error increased, really seemed to plummet down way below the desired energy, but CNN structure showed much more robustness against crosstalk errors. And this fully connected network showed a much poor performance if we apply other topology of qubit connectivity. And even with this structure on the right side, CNN really seemed to survive from those unitary error sources under a lot of circumstances. So we could clearly argue that CNN shows a better performance when these type of crosstalk errors are present. So to summarize, attaching a neural network to use VQNHE shows robustness against errors, especially bit flip error channels. And using a convolutional neural network on top of VQE handles these state-dependent unitary errors that are affected by its neighboring qubits exceptionally well. So it is very helpful when we use superconducting qubits as our quantum device to evaluate Hamiltonians. And on top of this, we suggest some future work directions here. First, we want to look deeper into the convolutional features and what those trained parameters of neural network actually means. We want to keep the role of neural network as minimal as possible so that we argue quantum supremacy on a scalable level as qubits increase. And as the original paper suggests, the amount of resource that is required does not increase exponentially as to the number of the qubits. But if the role of neural network is way more than just mitigating the errors, we can argue that the algorithm is mainly conducted by neural network, not the variational quantum eigensolver. So we want to limit the role of neural network. So we want to look deeper into the convolutional features by using feature evaluation techniques that are used in machine learning industry. And also we might try to evaluate more complex Hamiltonians like Heisenberg models, Fermi-Hubbard models, and apply a CNN scheme on those Hamiltonians to see if it really works well for more complex Hamiltonians and complex ansatz. Yeah, so that is that is pretty much all for our presentation. Thank you guys for listening, and special thanks to our mentor Luning Zhao for thoughtful advices and sincere support.
Thank you. Great talk. I'll open the floor for questions.
Hey, very nice talk. One question is like, are these IBM data, are these like the real hardware or these are the noisy simulators?
All experiments were done in a noisy simulator, but we put our effort into try to build a simulator that is as close to the real hardware.
I see. So IBM provides, I know IBM provides these like their fake machine, like fake hardware that mimics the noises. Is that the like noisy simulator that you use?
Oh, great question. We did not use a fake backend provided by IBM because we cannot adjust the parameters that we cannot adjust the error amount of errors. So we manually put in errors. Like for example, for ZZ crosstalk errors, we manually put in as you see right here, we have manually put in a ZZ crosstalk errors with an arbitrary parameters, and these parameters.
I see. So these ZZ gates are the like the error channels.
Exactly.
And then you design these so that the qubit that has like these ZZ error channels are are mimicking the actual layout of the like the superconducting qubit.
Exactly. Tang was responsible of yielding these parameters. He calculated these parameters based on the intensity of frequencies of the actual hardware and multiplying it by the time of the by the time it takes to do the actual gate execution. So those were calculated values, and we manipulated these values to increase the amount of errors.
Can I add some comment?
Please.
Hi, I'm Sang Lee from Orion team, and I actually benchmarked IBM Cusco's qubits, like some parameters like frequency or anharmonicity of superconducting qubit. And because frequency and anharmonicity and coupling strength actually affects the infidelity of each gate. So I successfully benchmarked frequency, anharmonicity, and I controlled coupling strength to control infidelity of each gate. Does it make sense?
Yeah.
Oh, thank you.
Thank you. We have time for another question if anyone has another question.
I have a question.
Please.
Thanks for your great presentation. Can I ask you about what is convolutional? Could you show me 2 slides before?
This one?
Yeah. No, next one, please.
This one.
Yeah, right. You talked about some convolutional features, so could you talk me more about what that is?
So by saying convolutional features, I mean we want to explore what those trained weights actually mean. We don't have any candidates for detailed technical evaluation techniques in detail, but we try to observe the what the convolutional network itself really does, the actual role of it, because we just, like I mentioned before, we want to limit the role of neural network to mitigating errors. So what we can do is we can try attaching a neural network onto a void quantum circuit, a quantum circuit that does nothing, or maybe apply only Hadamard gates and try attaching a trained neural network on top of it and see if it yields any meaningful result. If we detach VQE and the convolutional neural network still yields some information about the Hamiltonian itself, it means that neural network not only mitigates errors, but it does some meaningful things to lower the energy by kicking into the role of VQE. So we want to limit that role.
Okay, thank you.
Thank you.
Thanks very much. I wanted to thank all of the presenters. All your slides were great. Again, thank you for the presentation. And I want to say I thought everyone did really well answering the questions. I'll make sure to relay that information to Professor Kim. And again, these were recorded. Thank you again. I want to thank the mentors too for helping the teams try this mentored research experiment and project. And yeah, have a great week and thanks again.
Thank you very much.
Thanks, everyone.
Thank you all. Welcome to the mentored research.